All right, so kind of want to illustrate and kind of explain a subtle difference here, so you don't get too confused, because this part can be very confusing. What you should see is we have a double integral over S instead of a double integral over D, or at least the D that we are used to seeing. So normally what we would have is we would have some surface, whatever that surface is, floating up here in space. You know, we got this surface floating out here, whatever this thing is doing. And what we would normally do is we would have some kind of a projection down into the XY plane. And this projection down here, this would be our normal D. So down here, this would be D, where the surface itself is floating up here. That's S. The idea is that the double integral here, let's just leave that in blue. The double integral over S of f of xy dA is completely independent of the surface. So this part right here is completely independent of the surface. What do I really mean by that? It has nothing to do specifically with the domain that's projected down into. It's just the surface. That is completely independent. It is just the surface itself that we're talking about. So the whole idea about this is, and I'm going to rewrite this with a third variable now, is if I were to take a double integral over S of f of x, y, z, because x, y, and z is going to be part of the surface. Because normally what you would do is, if I gave you some f of x, y, you would say, okay, x is 1, y is 1, or something like that, or, x is 2 and y is 3 or something, and you would go x is 2, y is 3, and then what we would do is we would get out the value that's up here on the surface. That would give us the z. But now we're actually talking about some kind of an f of x, y, z, so now all of these points here on the surface are included as part of the function. This is going to be with respect to S. Okay, that's the f of x, y, z ds. But what we can do is we can parameterize this, because right now it's in terms of 3 variables. And remember, to do the cross products and everything, we need to get this thing down into the 2 variables. So we need to reduce this into a function that we can actually use. What we would get is a double integral of f of r of some other 2 variables. We're going to say u and v, could be theta and phi, could be r and z. It just depends on what we're using. And then the ds part, again, remember the ds part is the cross product of the partials. So it would be r sub u cross r sub v dA. But now here's the tricky part. This is over d. And I know you're probably saying, wait a minute, you just said it's going to be a double integral over s and not of d. That is true. But this d is not the same d as the one in the drawing. This d is not the projection which is down into the xy plane. This d now is the domain. This is the domain required to make up the surface S. So, once we do this, like let's say that we made this as a function of theta and phi, well, then it's going to be what domain of theta and phi is it that's going to get us to where we need to go. Do we need to go 0 to pi halves, 0 to 2 pi, whatever the domain is for that specific thing? It is not the projected domain down into the xy plane. That's what I want you to understand. So when we take this double integral over S and we put it into a parameterized form, it will then become a double integral over the domain needed to parameterize that surface. That's the main difference there. All right, we're going to go ahead and do a few examples. The last example will probably be its own video because it is a relatively lengthy example. All right, our first example says a surface S consists of the cylinder x squared plus y squared equals 1, and z is going to go between -1 and 1. So it looks like we're talking about a cylinder surrounding the z-axis from -1 to 1, radius of 1 for the cylinder. Together with its top and bottom discs, so we are talking about the top and the bottom, so it's the outside of the cylinder and the top and the bottom. Suppose that you know that f is a continuous function with f of positive and negative 1, 0, 0 equaling 2, f of 0 plus or minus 1, 0 equaling 3, and then f of 0, 0 plus or minus 1 equaling 4. Estimate the value of the double integral over s of f of x, y, z ds by using a Riemann sum, taking the patches of the S sub ij to be 4 quarter cylinders and the top and bottom discs. So let's kind of talk about what this problem is actually asking us, or what it actually means. What they're kind of giving us here is they're telling us that at some specific points, and they're giving us, looks like 6 different points, basically the point 1, 0, 0 or -1, 0, 0 is 1 unit out on the x-axis and no height and no y value, and they're telling us that that value is 2. Now whatever this represents, maybe it's some kind of a density function or something like that, they're not really telling us. Oops, would help if I can actually write the words density, but maybe this is some kind of a density or something like that, and maybe that's what it's talking about. They're not really telling us exactly what it is. They just want us to find the surface integral, so they want us to add up all of this stuff that's around the surface of the cylinder, and they are including the top and the bottom of the cylinder. So what I'm going to do is I'm going to kind of try and sketch this for you, but then we're going to take a look at it on Calcplot 3D as well, just to give you a really good idea. So we've got our cylinder. It says it's a cylinder. Let's see, x squared plus y squared equals 1, so it's got a radius of 1. So, something like that. And then it's got a height of 1 because z is 1 to -1. So up here and down here. So we'll say that that's 1. That's -1 on the z-axis. And we'll say that this is 1 right here. This is 1 right here out here. So the idea is what they want us to do is they want us to take this thing and they want us to split it into 4 quarter cylinders. So a quarter of a cylinder obviously is 1/4 of the cylinder. So, maybe we're going to split it, and who knows exactly how they want us to split this thing, but we're going to do it the easiest way that we can. Maybe they want us to split it right here at what might be, pi halves. Not at pi halves, like at pi fourths or something like that. Maybe we'll go 0 to pi halves, then pi halves to 3 to pi, and then pi to 3 pi halves, and so on. Who knows exactly where they want us to split this thing? But ultimately, what they want us to do is they want us to take it and they want us to split it into 4 equal pieces. And we're going to take a representation on each one of those pieces. So yeah, using the pi force is probably the best way to do it, although that's really not going to come into play. They're telling us that at, for example, the point positive and -1, 0, 0, what we have is we have some kind of a density or something like that of 2. So right here we've got a 2, and then back on the other side, someplace on the other side over here, we've got a density of 2. And then at positive and -1 for the y-axis, we've got a density of 3. So, out here, maybe the density is a little bit bigger. And then on the other side, someplace over there, it's going to be a lot easier when I show it to you on the calc plot. And then at the top and the bottom of this thing, right up there at the top, it's got an even bigger density. It's 4, right? So I'll make that even bigger than the green one. Now I'm going to go ahead and show this to you on the calc plot, and we should hopefully be able to see what's going on, and then we'll come back and actually figure out what the total surface integral of this thing is. Alright, so here is our cylinder. I've already gone ahead and put it all in there. Our cylinder that goes from -1 to 1 on the z-axis. what you can see is along the x-axis, I've got a little orange dot there right on the outside of the cylinder, and that is the point 100. It's got a, like I said, it could be a density or whatever it is. The value was given as 2, so I made it kind of a smaller orange dot. And then if I rotate this thing around to the other side, you can see on the negative x-axis at negative 100, it's got exactly the same thing because that's what it says. And then you can see here on the y-axis, at 0, 1, 0, I've got a slightly larger dot there. That's where the density or whatever, again, whatever this thing is 3. So that's representing that particular quarter of the cylinder. And then if I flip it around to the other side, flip it around to the other side of the y-axis, again, you can see it's exactly the same thing. And then on the top there, the z-axis, you can see that I have a much larger dot because it had the largest of the surface integral values. And then if I show you the bottom, exactly the same thing. So again, it's just kind of giving you an idea that those dots are representing each one of the pieces. So we have 2 different pieces of the top and the bottom. We've got one there and one there. And then what we have is we have the outside surface of the cylinder, which is going to be represented in 4 different sections. So there you go. That's kind of what I was trying to represent on the other picture.